Hey, also this is section 1.2, domain and range. And in this section, we're going to see three distinct topics. The first will be just the notation that we're going to use to describe domain and range, which will mostly be the inequality and interval notation. Second topic is domain and range itself from a number of different prompts, but they're all the same idea. And then the third thing is piecewise functions. So we'll be graphing those. This is the first section where we're seeing a graphing supplement with a homework. And so I'll talk about that a little bit more when we get there and show you where that is on the website. But this is one of those places in this course, there's a lot of graphing, and the computer does not do a good job of basically letting you demonstrate what you know, because it's really hard to draw on a computer. So it either kind of draws it for you, kind of halfway, you'll see what I mean by that. And then there's other ones where they're kind of matching. And so the graphing problems that I have to choose from are not fabulous. So anytime there's a bunch of graphing, I've put together a supplement for you guys to try, a paper and pencil one. And they're not due or anything, but if I put together a graphing supplement on it, on some topic, like in this case, piecewise functions, you are guaranteed they are on the exam. I didn't make them just for fun. It's stuff that I want you to know. It's the stuff that I can't have you show me on the computer, basically. But they are on the exam, so anytime there's a graphing supplement, you definitely want to check it out, and I'll show you those problems at the end of this video. Okay, so starting with inequality set builder and interval notation. I'm not going to go through all of these because it takes forever, and I'll do some examples with it in a second. But this little chart just kind of shows you every possible iteration of kind of what you can do with a 3 and a 5, basically. And so we have inequality notation, set builder notation, interval notation. Inequality is pretty commonly used, and so that one's good to be familiar with. Set builder looks scarier for sure. It's kind of like inequality, but like it got the tint package or something, and it just has some extra stuff going on. But they're basically the same. Interval notation, totally different game. This one is really handy in a lot of places. It's easier to write than this frequently. So we're mostly going to be sticking to these two. Let me walk through just one of these just to kind of point out the differences and the rules for them down here. So inequality notation, you should already be familiar with. This says 3 is less than or equal to 5 3 is less than or equal to x is less than or equal to 5. If I were to graph that on a number line just to kind of show what it would look like, we'd have 3, we'd have 5, and so we'd have a solid endpoint on 3 and an open endpoint on 5 because we're not including the 5. And it's the stuff in between that would be the answer. You may have also seen this with a bracket and a parenthesis, dependent on where you learn these things. But so this is the graph that would go with this inequality. Set builder notation versus inequality, it gets this brace and an X and a line, and other than that, it looks kind of like the same thing. And this is a more formal way of writing it. All this stuff is right here. It's read the set of X such that. So this would read the set of X, and the line is such that 3 is less than or equal to X is less than 5. Interval notation, what you do is you describe the interval using the endpoints. And so if the endpoint is included, like the 3, we use a bracket. If it's not included, like the 5, we use a parenthesis, and that's sort of our old open dot and closed dot. And we always go small to large, and so all that's right here. Interval notation, we always go small to large or left to right. Endpoints that aren't included, we use parentheses. Endpoints that are included, we use brackets. And then we get to these infinities down here, and I'll show you those in the examples. We always use parentheses because you can't actually get to infinity, so you can't include it as like an endpoint because there is no end. Okay, so these are some graphs to just practice the interval notation with. So this first one is all real numbers. And sometimes we'll see that written as, oh, you know what? I just thought of the thing back here. Forgot to show you these two. So the script R, that's another way of writing all real numbers. And then there's this funky little symbol that looks like a weird E, and that means element or member. And so for the all real numbers, this basically says the set of X such that X is a member of the real numbers. So that's kind of how that reads. But this little E, it just means that X is in that set. So not terribly alarming, but just it looks funky. And then there's our infinities. So let me come back to this page now, because that's basically the one we're doing here. And so on the computer, if we're putting this in, it would probably want interval notation. And out here lives negative infinity, out here lives positive infinity. So this is going to go from negative infinity to positive infinity. So that's one way to say all real numbers. And sometimes you'll just see it written with that bold R. But I think on this assignment, they're looking for this one. The next one, we're going from 2 to 7. I don't want to include the 2, so for that I want to use a parenthesis. And we do a 2, comma, and then up to the 7, and bracket. One thing about interval notation, I don't think I have an example that does this, but if this had been an open hole, there'd be a parenthesis right here. And then students often ask me, so if this had been open, this would look like this. Students often ask me, how do you know if that's the point, x is 2 and y is 7, or this? And the answer is the notation is actually identical. And the only way that you know is by the context of what that is being given to you as. So you're right. If you were thinking, well, doesn't that look just like an ordered pair? Yep, it does. But so it's just context. It's how you can tell them apart. For this next one, so this is going out to negative infinity. So that's my farthest point to the left, and always a parenthesis. And then up to 5, and parenthesis because of the open dot. And then we're gonna union. So union means or, and it's how we bridge a gap using interval notation. So I have this here or that over there. So 7 is included, so I want to switch to a bracket, and then up to 9 and close the bracket. This one, pretty basic, so negative infinity up to 8, and hard print bracket on the 8. For here, we're doing negative infinity to 4, and then our union to bridge the gap, parenthesis for the 6, and then out to infinity. And then lastly, we got, this would be 2 to 5, and then union that with 8 to infinity. Okay, so then we get to the domain and range problems themselves. We're going to see a few different prompts. This one's from a graph. This is also a place where people have a little bit of trouble, but it's a doable thing, and it's a fairly common thing to do. So let's see, find the domain and range for each graph, write the solution set in interval notation. As you're doing the homework, careful to read the directions. Sometimes they may ask for inequality, sometimes they may ask for interval. And so just making sure that you're reading and giving them the form of the answer that they want will save some frustration. So with domain on a graph, we're looking left to right. And if I look at how far my graph goes to the left, it's right there. And how far to the right is, it doesn't stop at 5. There's an arrow here. Even if the graphs don't show a hard endpoint like that with an open dot or a closed dot, even if it's just a line, it's implied it's going on forever. It'd be nice if they put arrows on there, but I think there might be something where they didn't. And so this is going to go from -4, and then we got graph all the way, right? There's going to be x values all the way to infinity. And even though it's heading like to negative infinity, it's going down, the x's are going to positive infinity. It's the y's that are going to negative infinity. And remember, for domain and range, domain, I guess I should have probably said that at the start. Domain is the inputs, it's the x's, range is the y's. It's going to be our outputs. And so basically what we're trying to describe is that interval right there, because this is going to go on forever down, but it's also going to the right. And so careful not to get negative infinity there. It's positive infinity because we're talking about the x values. Then when we talk about the y values, those are going negative. As x goes to positive infinity, y goes to negative infinity. And so our lowest point on the graph is going to be down there at negative infinity, right? Because this is just going to go down, down, down. And then as far up as it goes is right up to that 3. And when people ask me, is the 3 included? And I say, yeah, so if x was 1, what's y? 3. So the line counts. If the line is there, think of that as a solid dot, because that line is an infinite number of solid dots. So for our range on this one, we're going from negative infinity and up to the 3. And I just noticed my error right there, so let me correct that. I threw a parenthesis on that, and that should absolutely be a bracket. Sorry about that. For the next one, if we think of our left to right, so our farthest left is right here. Our farthest right is right there. So we'd be going from 6 up to 4. And then open dot, because we're not including, if I ask you what's the value at 4, it's nothing, it's not there. 3.99999 is there, but 4 isn't there. So this is going to go from -6, bracket because of the closed dot, up to 4, parenthesis because of the open dot. And then the range, and you don't have to draw this at all, this is just me trying to show where it is on the number line. The range, the low point is right here, it's included, and then the high point is right here at 6. So there's my high point, there's my low point. So the interval I want to describe is right there. Oops, it's closed. So this is going to go from -4 up to 6. So then question 3, find the domain and range for each of the graphs. Each graph in the library of functions introduced at the end of 1.1. So that was the last video where I was doing is the function one-to-one and what's the domain and range. So I kind of did number 3 as sort of a separate video, just for some more work with domain and range graphs. For number 4, we have, for the following relation, give the domain and range, indicate whether or not it's a function. So remember from last time, it's a function if for every x there's only one y, and domain is our x's, and range is our y's. So when they give us a list like this, all we gotta do is just kind of write down the numbers that are in the domain. It's not an interval because this isn't, if I thought of this, and here's 2, 3, 4, and 5. What it's giving is 2 is a value, 3 is a value, 4 is a value, 5 is a value. It's not saying 2.5 is a value, so it's not from 2 to 5 because all those things in between there aren't values that are given. So for the domain, when we have a list like that, and I think the computer will have the braces for you, so I don't think you actually have to type it. I think there's just a box in there, but it's braces because it's a list is the reason. Otherwise, if it was just say 2 and 3, then I wouldn't be able to tell it apart from whether or not it's an interval or just 2 and 3, or 2 or 3. And so then we just kind of close that out. The range, in this case, the range is always 4, so we just do 4. And then is it a function? Yeah, because we don't have any repeats in x. For each x, there's just one y, so we would say yes, that one is a function. For B, let's see, the input is a every time, whatever a may be. The range is 4, 5, 6, 7. Is it a function? No, because for when the input is a, I get 4 different answers. So that is not a function. So this next part is finding domain and range based on an equation. And there's a couple of restrictions here to be aware of. And this takes care of most of the domain and range troubles that we run into where we have to define what it is. First off, for a polynomial function, the domain is all real. And so that's anything like x, x squared, x cubed, x to the 4th, you know, with more terms added on. Those are all polynomials, and the domain on that's always going to be all real numbers, so those ones are pretty easy. Rationals, we have to exclude values and make the denominator 0. So if I have a fraction, remember we can't divide by 0, so it's those restrictions, of those variable restrictions that you might have seen in 98 or 8 point or 7.1 of 95. Square root function, remember on that we can take the root of 0, but we can't take the root of a negative number. We take the root of positive numbers also. So kind of the natural domain for a square root function is 0 to infinity. And so that means that this stuff inside the radicand has to be greater than or equal to 0. So let's look at that with a few examples and how that would look. So first one up is a root function. And for this root, we would have basically this in here. I can only put in x's that keep this bigger than 0. So for instance, if I put in 3, I'd have 6 minus 9. That wouldn't work. That wouldn't be in the domain because I get negative 3 under the root. So we're trying to find all the numbers that basically don't do that. And the easiest way to do that is just to solve an inequality. So we're saying 6 minus 3x needs to stay greater than or equal to 0 for this thing to be valid. So then solving this out, I'll just shift my 6 over this side. So that gives me negative 3x is greater than or equal to negative 6. And then there's this step right here where I divide out the negative 3. And if you haven't done this for a while, you might have forgotten that you need to flip the inequality when you divide or multiply by a negative. And so that's going to happen. So this would be x is now less than or equal to 2. If I want to give my answer in interval notation, for me, I'm always kind of thinking of the graph. When I do interval notation, it's just easier for me to get things in the right place. You certainly don't have to graph it, but that's kind of what I picture in my head. So x is less than or equal to negative 2 would go from negative infinity and then up to 2. And we want to include the 2. As if x was 2, 6 minus 6 would be 0, square root 0, 0. B, so this case we have a rational function, so that means it's a fraction. And so what I want to do is factor this piece. Basically I want to take that piece, whatever's in the denominator, and set it to 0 and solve whatever it is. And since this one's quadratic, it's going to involve factoring. So we can go x minus 3, x minus 4 equals 0. So then just solving it would be x equals 3, x equals 4. But these are what x actually can't equal. So I should probably do a little not 0, because those are the two numbers that if I put them in the denominator cause division by 0. So those are the bad numbers. So if I want to describe this in interval notation, it's a little bit of a pain. So what happens is, basically I have a number line, and I have 3 and 4, and those ones are open dots. And what I'm trying to describe is everything but that. And this is where the set notation is actually really nice, because we can just say set of x such that x isn't 3 or 4. So that would be the way I would prefer to write it, but I think that's a really bad comma. I think the way the computer wants it is the interval notation, so it's a little cumbersome, but here it is. We go from negative infinity up to 3, and we don't include the 3 because it's an open dot. So then union 3 again, so we said everything up to 3 but not 3, and then everything after 3 is still not 3. That up to 4, union, and then 4 to infinity. So for C, we have a root in the denominator. So the root has to stay greater than or equal to 0 under the radical, or it's imaginary. But this radical happens to be in a denominator, so that means I need to dump the equals. Because remember, this stuff needs to be 0 or positive, but for a rational function, the denominator can't be 0. So that's going to eliminate the equals. So this is going to be greater than 0. You kick the 3 over, x is greater than negative 3. And so that would be going to the right. So that'd be negative 3 to infinity. For D, D's a little tricky. So we got two different things going. We got the numerator with the root, and we got a denominator with a 0. So first thing is x can't be 5, because if x was 5, 5 minus 5 would be 0. So 5 is out. And then the next thing is this can't go negative, so we got to say x plus 2, this time greater than or equal to, because it's in the numerator, 0. Kick the 2 over, and we get x is greater than or equal to negative 2. So let me just kind of do a quick little sketch to kind of help orientate our brain. So here's 5. So I got to exclude 5 because that would give me division by 0, and I want all the stuff that's greater than or equal to negative 2 except the 5. So it'll be a solid dot going that way up to the 5 and then to infinity. So that looks like negative 2 up to 5, oops, bracket, sorry, negative 2 and then up to the 5, parenthesis, union, parenthesis, 5, up to infinity. So the last topic in this section is piecewise functions. I'm just going to do a little example, not in the notes, just to kind of try to introduce the idea of a piecewise function. So if you think about if you had a job that paid 20 bucks an hour, that's going to be good from 0 to 40 hours, right? And let's say after 40 hours you get time and a half, so instead of 20 you're going to get $30 an hour. So if we just think about the graph, what that would look like, between 0 and 40, the slope come up something like that. And this is hours, and this is how much money you make. If you work 1 hour, you get 20 bucks. If you work 2 hours, you get 40 bucks. So that's kind of what's happening with the graph. So the slope of this graph, m would equal 20. But then at 40 hours, something else is going to happen, which is you're going to get time and a half, you're going to get overtime, and then it's going to be a little bit steeper slope, because now it's going to go for $30 an hour since you're getting time and a half. So now we'd say m equals 30, and there just isn't a way to write that without writing two separate functions. And so what we do is your pay is going to be, the easy equation would be 20 times the number of hours you work, and that's going to be good on the interval 0 less than your pay, we'll call that x. I guess I should call it h for hours there, less than or equal to 40. So this equation would be good from 0 to 40 hours. The other equation, which isn't really 30h, I would need an offset that would be down here, but I'm not going to bother to find it for the sake of this problem. So 30h plus some constant down here somewhere. That would be good for when the h's are greater than 40 hours, because that's when you're going to get overtime pay. So that's kind of the idea of a piecewise. So it's going to have a what you're going to graph, and then a where you're going to graph it. And we're going to have at least two functions, and it can be more. So let me show you what the examples on the homework look like. So this one is giving you a graph, and it's giving you sort of which function is which function, and it's asking you to fill in the where it's happening piece. And the notation they're using on this one is a little bit funky. We don't usually use the member symbol or interval notation, but I'll show you some coming up that look a little bit more standard. So this is saying x is -4, or y, actually output y equals -4 if x is what? So we look here where x is -4, and it looks like between -6 and -4 is the values. So this would be from -6 to -4. And then y is 1 if x is, so it looks like anything between -4 and 3, not including the endpoints. So we want to use parenthesis, -4, and then up to 3, close parenthesis. And it's going to be 3 on the interval 3 to 6. So that would be from 3, oops, that one should be a bracket because it's solid, up to 6, and a bracket. So this next one is asking us to find the function value based on the graph. So it happens to be a piecewise, but it could have just been back in that first section. So when f is -5, or when x is -5, finding f of -5, we come out here to -5, and it looks like that's going to happen at -3 right there. F of -1, x is -1. So this is a little bit of the funky part where one side has a hole, the other side has a solid dot. It has to be that way, otherwise it's not a function, right? Because it would hit the graph twice. So any of these endpoints, you're going to have that where there's one solid, and then there has to be a hole for the other meetup. So in this case, if we're looking at -1, our value would be 3 up there where it's solid. And then for 2, it looks like x is 0, or sorry, y is 0, pardon me. For number 8, we have find the following values for the piecewise, and this is about more what you would see for the notation for if right there. So f of -2, that is when x is less than or equal to 0, so we put it in the first equation. So f of -2 is going to equal 3, and then times -2 minus 4, so that would be -6 minus 4, or -10. For 0 equals 0, so that's this equation still. 3 times 0 minus 4, and oops, I don't know what that was. So that's 0 minus 4, or -4. And f of 2, that's going to be good for this one, because this is where x's are greater than 0. So that would look like 2 squared plus 1, or 4 plus 1 for 5. Okay, these last three are the ones that go with the graphing supplement. I'll include a screenshot here to show where that is. So to find the graphing supplements, you just go to the course page and then blank PDFs, and then course pack exam 1, and then here's the whole course pack if you want to have a blank one, and then here's all the graphing supplements. Okay, so for number 9, what we're going to do is, instead of fx, I'm going to call this y, just because I think it will seem better for graphing purposes than f of x. So I can put in any numbers I want between -4 and 0. So let's start -4. -4 plus 4, that's going to be 0. Square root 0 is 0. If I put in -3, that one's pretty good. -3 plus 4 would be 1. And then square root 1 is 1. Not so stoked about 2, because 2 would give me, or -2, sorry, would give me a 2. Square root 2 isn't good to graph. Same thing happens if I do -1. I'd get -1 plus 4 is root 3. Also not that great to graph. So let's go up to the 0. So 0 plus 4 would be 4. Square root 4 makes 2. And this is a place where that library of functions video, I was saying there's three of the functions you want to kind of know heading into both this section and in 1.5 coming up. And one of them was the root function, one is the absolute value, and the other one's the square function coming up in question 11. And so if you already kind of know what that should look like, it's sort of that half, it only covers half the graph and it kind of climbs slowly. That's what we're going to see here. We're just going to see it shifted over 4 units. So -4, 0 would be right there. -3, 1 is right here. And then 0, 2 is right there. And these both have equals, so I want to use solid dots on my endpoints. If you wait until after 1.5 to try the graphing supplement, you're going to be able to look at this thing and know exactly, you're going to be able to do it without a table. You'll go, okay, so square root looks like here, here, and here. That plus 4 inside shifted it 4 units to the left. So there's definitely an argument for holding off doing this until you've seen transformations in 1.5. But for now, I'm just going to approach it like we're just plugging in points into equations. For the second piece, we got this x plus 5, which will probably look better if I write it as y equals x plus 5. And that just kind of feels like a linear equation. We could make a table for that if we wanted. I'll go ahead and do, let's do that for a second. So I'm going to put in 0, which is the number it says not to put in. And I'm just going to write hole. That's going to be a hole in the graph. But I need to know where to put the hole, so I'm plugging in 0. I get 5. So that means when x is 0, y would be 5 if it was defined, but it's not. So that's where we put the hole in the graph. And if I put one more, point, so let x equal 1, 1 plus 5 would make 6, and there's our second graph. And so with this, you can see it is a function, because if I draw a vertical line anywhere, I only hit the graph once. You have to be careful on the boundaries that you get a solid dot in one spot, hole in the other where they're meeting. Otherwise, it's not a function. So then for number 10, this one's a little bit different. So we have x is 3 for any y is 3 for any x is less than -2. So this f of x equals, again, I'm going to call it y equals and then 3. And if you haven't seen one of those for a bit, it's a horizontal line through 3. So what this means is it doesn't matter what x is, although it does have to be less than or equal to, or less than -2. So I'll go -2, -3. And again, I'm just going to write whole right here to remind myself that that doesn't have an equals. And it's always going to be 3. It's that constant function. It was the first one from the library of functions. So when x is -2, y is almost 3. And when x is -3, y is 3. And so you can see it's going to kind of like do that forever. And then this one we got in the middle is an absolute value. So it's going to look like this. Y equals absolute value x minus 1. And this is good for numbers between -2 and 2. So let's just throw them all in. So negative 2 in absolute value comes out positive 2, and then 2 minus 1 will be 1. Negative 1 would be 1 minus 1, 0. Absolute value is 0, minus 1, minus 1. And you can see we're going to get the same numbers, right? So 1 minus 1 is 0 again, and then 2 minus 1 will be 1. So that's going to be right here. So when x is negative 2, y is 1. And then it's going to come down like that V shape that we saw in the library of functions. And again, if we waited until after 1.5 to try the graphing supplement, you'll be able to look at this and you're going to know it's the V shape and you're going to know it's shifted down 1 unit. And then you can just draw it right in place and not have to make a table. I kind of like doing the table version too, just to emphasize the domain piece, because that's the domain is where people have troubles. And our last function would be y equals x plus 1. So that's good for x is greater than 2. And so I'm going to put 2 in, and again I'm going to write whole to remind myself. So if this is 2, 2 plus 1 would be 3. If x was 3, 3 plus 1 would be 4. So when x is 2, y is 3, and that's a whole, so we're going to do like that. And then 4, and it's going to just keep going up from there. Oops, as I was setting this down, I just noticed I graphed that off 1 point. So when x was 2, y should have been 3. So I should be right there. Sorry about that. Okay, number 11, last one. So this would be y equals negative x minus 2 xy. So good for x's that are less than negative 2. So I'll put negative 2 in anyhow and write a whole. And that would be negative 2, so it would be like that, minus 2, lots of negatives going. So that would be 2 minus 2, or 0 for that one. And then we'll go negative 3, or we could also graph using slope and intercept from there. We don't want to use the intercept, we could use the slope. So negative of negative 3 minus 2 will be 3 minus 2, or 1. So let's see, when x is negative 2, y is almost 0. And let's see, negative 3, 1. And so it's just going to continue up. Kind of like that. And then we got 5. So this is only for x equals negative 2. So it's y equals negative 5, but just for the negative 2. So that just means we're going to have a point on the graph, just one single point. So that's going to be up here at 5 and 2. And then our last one is x squared. So if you learned that from the Library of Functions video, you can just come over here and draw it right now. But you want to get where you do not need this table for section 1.5 for sure. So this is good for anything negative 2 or bigger. So I'm going to write negative 2 in a whole. And then negative 1, 0, 1, and 2. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, and then 1 and 4 again. So that's going to be a whole right there, dot, 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 dot. You want to get where you can just do like you saw I wasn't looking at the table, right? So I'm just going, basically it starts here at the base, over 1, up 1, over 1, up 3, over 1, up 1, over 1, up 3. More of that to come in 1.5. And then that would be it. So that concludes domain range and then some piecewise functions. So again, definitely check out the graphing supplement. If I bother to make a graphing supplement, that means it is positively, absolutely, without a doubt on the exam. So definitely give those problems a try.